was a little bit confused about or I think about that's not really about operating R or doing those basic R programs and those code that already provided to you. It's more about how to read those R tables. Right? So So for again this lecture, we were quickly review what's been just been last week about the cheat sheet, right? So suppose I fit a linear regression model, which is the OLS model, or the least square model. That was the protagonist for our last week's lecture. So I fit like the linear regression model that regress. Oh, by the way, about terminology, I think you're probably learning this somewhere. So usually it's on econometric textbook if you're an econ major. They usually kind of describe a set of relationship between a set of linear predictors this way. So suppose you have a y variable, right, and a couple x variable. So just like this case here, we have two variables. So they usually describe that I regress this on your explanatory variable, or simply pretty much anything on the right-hand side of it. So that's pretty much how they describe the data, describing the model equation. Okay? I regress, let's say I regret, even though you incorporate the outcomes as you expected, you say that I regret or formulate this model. But anyway, it should be I regress. This y variable can be anything for example, like the median value of urban housing. The static explanatory variable is how they describe the relationship between the outcome variable and the explanatory variable. So here I regress median housing value and crime rate and parent-teacher ratio. The two on the right-hand side of it are my explanatory variable. And here's what I got, right? So you'll see that there's or actually see that there's a software package, but not properly. They call it pivot table. I think the name is really weird. Anyway, so here we're going to see there's a table, right? Got first column is estimate, the second is standard error. The third one, t-value, followed by p-value. Right, so we're definitely given the p-value a couple moments later. So what exactly is estimate? Just try to imagine a scenario. You just walk in because you're late. Walk in a conference room and your supervisor discussing the your case analytical result, and then because you just got in and you have absolutely no idea what's going on here, and they just put this on the table and ask you to tell it. No, it's simply asking you to tell him or her the finding. Or can be gleaned? What information can be gleaned found in this table alone? Suppose that you don't know anything about this whole things. You want to take this one? Actually, this picture actually offers lots of information. Well, so at the 2-year lab, there are a number of variables including the model, right? I put two explanatory variables into here, so there's crime rate and parent-teacher ratio, right? And estimate is simply their data. There 1, there 2. Say that, okay, so both of them had negative impact, right? And it seems that the crime rate had almost like twice or thrice, the 3 times the magnitude of effect relative to parent-teacher ratio. And the third insight that you can get from this output is that by what metric, or what standard can you make this claim? Are those important variable? Are they important at all? You could say yes, because I have standard error. But standard error alone doesn't explain anything, right? Because you could have maybe like trillions of, but you need that the beta coefficient is a trillion, something like that, and you should probably go down and fix your model. Right? So I should also look at t-value, because t-value is simply is calculated as your beta coefficient divided by your standard error. Right? So assuming normal distribution, right? So you have the t-value is larger than 2, meaning standard 2 standard deviation away from the mean. Simply that should be a uniform mean. So that's 0, meaning that there's no relationship between two variables. Then you can say, I can say with 95% certainty that prime rate has this amount of effect on median positive value, right? Instead for parent teacher ratio. And at below this table, it offers you a guide about how to explain your finding in certainty term, right? So those are, I will say, after you get really proficient with using R, or pretty much all kinds of statistical package, the only thing that you will look at is the star sign. That will tell you how happy the model is with the data in your statistical model. And also, there's another thing that we haven't seen before, like that's statistic. We will get to that in today's section. And another thing to look at is, all right, so suppose you don't know anything about data. What's the size of this data? I mean, like, you just walk in the conference room, you don't know anything about data. Can you, oh, go on, take it. No. You should simply, because you have two variables, right? So you allow 2 degrees freedom. And that's the remaining degree freedom. And also, don't forget that you must always subtract one from it because that comes from your equal variable. So that should be 347 plus 2 plus 1. That's 400. You have the 400 observation.
Yeah, so it's 300.
Okay.
I say 300, please.
Okay. Okay. So that was it. And now we get to the p-value chains. Right, so assuming normal distribution, right? So suppose you were saying that it was like 68% of the data are clustered around the mean value, and how the normal distribution is 0, right? And I want to put that the relationship is either negative, positive or negative. And they are, I also want to demonstrate that they are significant, meaning that they're significantly away from the mean value, the normality mean, right? And we know that in order for so for the foreign data that so in your estimate, suppose the data is generated through random draw, right? So I mean, I purposefully pick data point that's extremely high, right? So if you want to measure, say, the human height, the younger generation. So you wouldn't go to a class that's full of to a student that belong to the basketball team, right? So because they are normally high. And you wouldn't say that, okay, so they represent our country's average male height, right? That's incorrect. So suppose all the data generated from random drops. And the probability that I will get a data that's as extreme as this one, that's what I find out through the, here I'm showing you the coefficient plot, right? So the dot means your beta estimate, while the whisker is your confidence interval calculated through standard error. Okay? So you have a truly wide confidence interval. That means that okay, so perhaps the estimate is it's a little bit uncertain compared to this one. Right? It has a narrow confidence band. Right? So we want to evaluate to what extent are they away from sample mean. Right, so here's what we found. So suppose in our situation, suppose we got data that states 3 standard deviations away. Suppose we got a coefficient estimate that is like this one. If it's divided by standard error, it's 3 point something, meaning it's at least 3 standard deviations away from the uniformity mean, right? And then that means because the cumulative distribution, say here, do I have all the colors? Cumulative distribution function, meaning that you will observe a value of that 3 standard deviation away. As extreme as this, by chance, on the normal distribution. Meaning that by chance, meaning that the true means could be 0. Right? Meaning that there's no relationship between x and y. Because the beta term is 0. Right? So suppose that's my null hypothesis. Right? But because the reason that you run statistical model, if you want to prove that, you want to demonstrate that there's some relationship between those two. So the probability that I will get estimated value as extreme as this one, by chance means that the null hypothesis HO is true, is this remaining one. So if I really get a very extreme value, right, that is extremely skewed to the right, right, and have the cumulative distribution function right here, it's already like 99.7 something, right? So the probability that I will get this by chance under the null hypothesis that there's no relationship between y and x is simply 1 minus cumulative distribution. Should be like something. This is very low, so that my claim is actually backed up by some empirical evidence, and the probability that I will be wrong is very low. Right? So that's how they interpret p value and t value and all that kind of stuff. Okay. And because in just probably in just a couple months, you will just see this other thing jumping out because we have the election going on, right? You see, right? So the survey is calculated. It's based on a random sample from blah 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 population, and then we have, and the finding is distributed on, say, to 95% confidence interval, something like that. Okay. Right. So I will give this to you so you can play around with all this and try to familiarize yourself with the statistical jargon. Okay. So we're getting to this class. Good. Right, so we'll actually begin with statistics. again, like last time, if you haven't installed the attached package for this course, official textbook, Introduction to Statistical Learning in R, then you should, if you already have installed that, it should be called require or use library. Right? So the first thing to do, whether you're familiar with R or not, is simply to take a look at your data, or simply if you download from some third-party device, you should also check out your data. What's inside the data, right? So for here, it means that, so if I type data equals something, that means the data is probably attached to some pre-installed packages or third-party packages. And then you need to code data to retrieve those data, your attached data from those R packages. And then you should take a look at the variable name means what variable does this data have? Simply type names and then goes with the name of your data. Another quick way to check the dimension of the data is simply type did or dimension. So you will see just as this one through. See is you have a data set of like 400 observations, 11 variable, right? You can actually see the summary of the data by typing summary, and then you will find this quantile distribution of the data. And then in one of the questions that I posed on today's slide, says how is the cell variable, right? The cell is one of the variables inside the data. How is that distributed? Right? Another quick way to give you like a quick visual check of the data is that you can plot the histogram, right? Simply type his and then you close that with the data. But because the variable is attached under this data set, and then you need to enter the dollar sign to subset the variable from the data. But that doesn't always work. I will come to that pretty quickly. Right? So if you type histogram, then you will give you a quick visual check about how the data is distributed. Well, it's slightly uniformly distributed. But you may not always be able to do that because, well, all this data are numerical data, right? But things happen there, so like many of your other colleagues or classmates who are so into the subtopic of the text mining, they're primarily nominal data. And they say, I want to plot a histogram or continuous distribution of those nominal data, and you would probably receive an error message. You couldn't do that on nominal data. Now you can use what you have just learned last week to fit the model. And there are a couple ways to do that. And each of them come with its, shortcoming. So the most traditional way is simply type LM in your regression model, your y variable, and followed by a tilde sign, and your x variable, right? And then you specify where does this data come from, right? So that you do not need to subset the data. Another way is that, okay, so you can say, I always forget to type this argument, the data, because I have a hard time remembering where this data comes from, it's affiliated package. So in other ways that, well, we can subset the variable from the data set, right? So that way you do not need to specify the data source. Because by doing this step, you're really done. Now, more lazy ways that, okay, so you say for the purpose at hand, for example, oh, by the way, I forgot to mention, if you check our service, so this way you're going to distribute your first assignment. So I will distribute that by email. Okay? Tonight. So you can say, okay, so for this week's assignment, I only need to work down this particular data set. I won't need to process all the data set. So there's very low probability that I will get mixed up. It won't be that messy. So that's good. So you can use this shortcut by telling R that I'm going to attach this data on the global environment. And then so pretty much every command that I type on this console should all come from this data set. So that way you also do not need to specify your data source, right? So just a couple commands. Right, it's very easy. And then after you're done, you can say detach, and then you will return back to your original setting. But the chances are people always forget that, okay, I forget, and after maybe like 100 lines of code, you say, I already forget I have attached this on the environment, so that you sometimes won't be variable name is identical to other stuff that is just generated through your outcome, so then all will get mixed up, and that's bad. Right. So after you're done, then you can put summary or print to print out your output, which we have just seen. Right. And then there's a quicker way to plot the result. You can say, all right, so I want to plot the distribution of the data since I'm doing a bivariate regression, right? So the regressing cells on tracks. So I want to put my x variable tracks against to evaluate distribution against my y variable cell, right? So this is how you plot a bivariate plot. It's simply using the plot command. The plot command is actually more versatile than you think. You can simply enclose your model output inside plot, and then you will generate a bunch of plot. So you click on the screen. You can try this actually by enclose your model output, say ln fit inside plot, and then keep clicking on the screen. And so here's a couple arguments there. I already mentioned that last week, but we can just review it. So it's just say, so what is CEF? Sexual or something? No. It means the prime size here. So you can adjust the size that you want to display. It's actually one way that you can cheat your viewer, right? Actually, if you want to demonstrate, okay, I want to show that the data point is actually more clustered, then you can actually make the point size larger, right? So they kind of overlap with each other. And PC edge means point shape. But here I'm using the default one, just circle, right? You can actually just say, I want to do triangle or square. That's what I would do, right? Also the color, simple colors would be the color command. But you can also set a type, right? So here. Now AB line is simply the 45-degree regression line. You can put it out this here. So suppose that they are actually perfectly, no, so suppose two variables share a perfect negative or perfect positive relationship that should be cut across half of the plot. And the A beta is always mentioned after your plot command. Right, you can add something plot A beta and then followed by plot command. That won't work. And actually, one of the questions that I got from last semester, last year, a student actually at a very end of the semester, the company said, all right, so all you tell us to do is simply to do a bivariate regression. I said, no, actually, what's usually how to do multivariate regression? Because I don't know how to include additional variable into the model. Or simply type the plus sign followed by other variable, and you can keep adding variable into it. It's very simple. And then we can see in the third model, we also add the third variable into it, so you can keep adding variable into it. And then you can compare their performance by reading those relevant statistics. Right? Now we can back to our lecture part. And also, there's something that is simply haven't received much attention about the beta zero of here, or commonly called common intercept. Here. So if you look at the R output alone, you'll say, so what is this guy? I never recognize this guy. Well, that's your beta zero, right? We call it baseline effect or common intercept. That means that no matter what's the value that's taken by those explanatory variables, it's going to have this amount of relationship on the dependent variable. I mean, you can try to think about human height, right? So someone can be extremely tall due to better genetic or better nutrition, and someone can be probably below average, height below average. But I mean, you cannot have 0 centimeter in height, right? So there must be some baseline effect. So that's here, the common intercept. And if you do not want it to show on the graph, what can you do? I mean, in R. Well, you can simply type -1. So here it should say price while advertising -1. Then you will remove common intercept out of your R output. Okay? And since I already covered this, how to infer the degree of freedom in the data. And what's the total sample size? So here, is that all observations have a common intercept as well, exactly what we got. And that's the baseline effect price, right? You cannot, you see a car that's 0 in price, well, that's probably your parents give you one. But you will purchase from a car dealer, then they wouldn't charge you like $0 for it, unless you're robbing it, right? That's illegal. Okay. But it seems that we also encounter something new in those R output. For example, receiver standard error. That's what you were seeing here. Receiver standard error. But what is that? You say, okay, I don't know what standard error is, but what is receiver standard error? Right. I know what standard error is there. Right. I know what's degree of freedom. Right. But what is receiver standard error? And what is R squared? And the relevant question to add is that, right, it seems that if I keep adding variable into the model, then that should improve, more or less, the explanatory power of my model. So why not just keep throwing lots of variable into the model? Should we keep adding more variable into the model? Right, so this question is related because you can actually use this to adjudicate this decision. So suppose you're fitting a multivariate regression, means that regression has multiple variables, right? More than one variable into the model, so you're doing this, right? Fit 2 variables into the model. You can also fit 3 variables into the model. So there has to be a criteria to decide which model works the best, because from what we have just covered at the very end of the last lecture, so they have Gauss-Markov theorem and blue property of linear regression model. So the first one, the blue probably is the best linear unbiased estimated. The first one is the best. What is best? Meaning that we should judge that on the efficiency criteria, meaning that model is best because it has minimum variance. Right. And also, you also only need to fit a small amount of variable to explain the largest variance in the data. So as I said, less is more. So there has to be some criteria for us to decide how many variables should we put into the model, not just keep throwing variables into it. And here is what the MSE comes out. Is the mean square error basically is the refer to the average of the square of the error, or simply is the square is the average square differences between the actual value and the predicted value. Let me just erase this. Right. So open our frame. Okay. So predicted value, the actual value. Right. So least square error. So we square that, and then divide by some remaining degree of freedom. Average square differences between estimated value. And then RMSE, the other thing different is the R. It's simply the square root, which is the root mean square error of the above term. So it's usually known as standard error. That's what we will see on the R output. And the differ from some relevant concept is called, usually differ from what you probably heard from descriptive statistics called standard deviation. Standard deviation is calculated from simple variance, right? Meaning that you have not put any X variable into the model, you simply look at the outcome or the observed value, right? It's called simple variance. And if you square that, that's the standard deviation. And you can use the root mean square error, this the standard error, to calculate the confidence interval that we just I have just showed you on the coefficient plot. So if you look at the CARC data, go to our page, you can see this following thing, and you can actually calculate it all by hand. So what is RSS? That does not mean that, okay, you could, I want to put this website on my RSS. No, this should be interpreted in statistical term. It's called sum square, sum square receiver. Means that all the receiver from the model, sum square receiver, right? So it's something, well, actually here I call it a receiver sum square. So it's calculated as the sum of the square of the differences between the real observed value minus the predicted value here. Okay. And you simply put a summation sign and sum it across all the observations in your data. Okay. It refers to the proportional variance that has not been explained by your predicted value. Right? Because, as I demonstrated last week, you simply try regression. Linear regression is you're trying to capture the shadow of the object hovering about by projecting a line with some slope equal to some your estimated coefficient at beta amount. You try to capture as much variation in the data as possible. But of course, there's definitely some, because we like the conjecture thing, so there's definitely some error, small amount of error, it could be large amount of error to doing this pattern. Right. So that means the amount of error that wouldn't be able to be captured by your predicted value, by your statistical model, under the normality assumption. So usually the receiver sum square had chi-square distribution with the continuous distribution with n-2 degree of freedom, meaning that because you lost 2 degree of freedom from y and x, right? So the expected value here is the variance distributed n-2 degree of freedom. But of course, if you simply look at this alone, we will know immediately that if you're dealing with a large data set, you usually have a large biases. Why is this the case? Well, I already highlighted for you. Anyone? Well, because it's an increasing function of sample size. data size, right? So it may not be a good estimator for those variance statistics for large data set. So that's one caveat that you should look at. Right, and rather the concept called receiver standard error for RIC, it's simply just the square root of RSS divided by its corresponding degree of freedom. It's also known as receiver mean square, RMS. Right, and here, because we only include one variable, and we also lost 1 degree of freedom from the y variable, so that should be divided by n minus 2 is your sample size. And if you get a sample size large enough, it should converge to this. So you have the expected value of sigma squared. We usually write it as sigma squared. That is an estimable variance. So, so the sigma squared gives an unbiased estimator for the error variance in your regression model. And in the case of multivariate regression, here I'm only doing the univariate regression, means that I only include one variable into the regression. That's predicted for one. Of course, you can include more. And then this relevant chi-square distribution statistic will be your sample size minus n variable minus one compound r. Compound y variable, we all have variable. Right, so we already have this, right? So we know that the receiver sum squared is the proportion of variance that being left out or being left out in our regression between y and x, right? And our explanatory variable x was able to capture certain amount of variance in y. It's only that it's not perfect, so there's what was being left out is captured by simply being sum over all the observation and crystallized into RSS receiver sum squared. Right. So the amount of variance being captured by our explanatory variable here, x plus x times beta, is usually called MSS, model sum squared. You know, that's the variable that we put into the model. Right. And together, this two part should equal, well actually it's perfectly equal total sum squared. That's all the variance in the data. So the variance, as we know from last week, come from the differences between each observation and the overall mean. Right, so that's why I draw this here. So actually I should put a y here. Should be the sum of the square differences between each observation and the overall mean. So suppose we have, say, we have someone who stands at 161 centimeter, another stand at 175 centimeter. We took this measure from 10 students, and the average height is like 170 centimeters. So we know that the differences in the first observation, the way this deviation found from the sample mean is like 5 centimeters, right? And for the second observation, it's like 9 centimeters. And since we of course say, no, it's negative 9 centimeters, but of course, but since we'll be doing square, right? And square that over, so that doesn't matter. But the most important thing to know is that this part, the first part, refers to the proportion of variance that being taken care of by our explanatory variable that we put into the model. While the RSS, receiver sum squared, more like a receiver term, or in a status receiver, you absorb all the unexplained variance in the data. Okay? So before we get to another exercise, any question here? Okay. So here, to show you, give you a real example of how this goes. So suppose we got this observed value from a really small sample to like 5 by real number, real positive number, at 3.35548, right? And also suppose we fit a regression model and give each of them an estimate, a linear estimate. Right. So the residual sum squared is simply the square differences between the actual value and the predicted value, right? You can do this for each and one of the 5 observations, right? And then you sum them together, right? Procedure sum squared. Here we forget the total sum squared. We refer to the previous page. It's simply the actual value minus this the square difference between the actual value minus the overall mean. So, will anyone calculate the overall mean for me? Well, it's 5, right? So you can just substitute 5 into y bar, and then you would get this. Right. So now I have all the relevant statistics I need to calculate all those previous distribution statistics. I have RSS, TSS, so the MSS can be easily derived. So another thing that I have talked about is R squared. So what is R squared? Very simply, just square something. Yes. So if you go back to the page, you see multiple R squared, meaning that the R squared is a multiple regression, multivariate regression. So it's at 0.28. What is that? And also, well, because it's a value that's strictly below 1, right? It's probably bounded between 0 and 1. So, like, whenever you see a value like this, then it must be some statistic that bounded between 0 and 1. Right. So what is it? Well, it's actually a measure of the proportion of variance being explained by the model that you fit and you throw into your statistical package. Right, because you know that TSS minus RSS is MSS, model sum squared. And MSS means the proportion of variance in the data, or in Y, right, your outcome variable. That's being explained by your explanatory variable, by your model, right? So very intuitively, R squared is just a measure of how much the total variance, how much of the TSS that being explained by the variable that you put into your model. Right. So a lot of times, so probably for the longest time, before like 20 or 30 years ago, this discipline, especially a sort of science scholar, so fascinated with trying to get the highest R squared as possible, because they believe that, oh, okay, so if my statistical model, the model that the variables I include variable that I try to tell my story. Say this, for example, does inequality or natural resource distribution help explain, say, interstate war, like what's going on right now between Russia and Ukraine. Right, so you say, okay, so if the variable I put into the model have to account for the major variation in the outcome variable, say war, interstate war, then that must mean my theoretical model is very good. But I mean, in the last 20, 30 years, things has changed. But people are more fascinated with fixed, studying these small things or improving your model instead of simply look at Osberg. The Osberg is simply influenced by lots of things. For example, like if you have variable that's, say, if R and Y, if your explanatory variable, one of your explanatory variable is X, and your outcome variable Y is somehow is nearly perfectly correlated, then by default, you're going to get really high R squared. Right? So that's influenced by the variable that I put into the model and something that you just don't know. Right? So think about like geographic continuity. You say that, for example, you try to study the probability of interstate war. It seems like some countries never fought each other. Then you ask why? Well, because they did not share any geographic continuity. Because their borders did not categorize each other. That's why they have no chance to fight each other. For example, you really imagine that like a country like Russia would declare war with some microstate lying in South Pacific, right? Because they're so far away and their border do not cross, right? So they are influenced by the variable you put into the model, their functional form. You can definitely improve your R-squared theory by trying to capture as much information. We'll actually get into this in the second part of today's lecture. Functional form. How to use functional form specification to capture major variation in outcome variable. So you can say, maybe the relationship isn't exactly linear. Maybe this serves as a curvilinear relationship. So I should put it, I just square my explanatory variable. And then actually how to capture this band, this quick jump in some range of the data, right? Also, their correlation, right? Because you can inflate your variance covariance matrix. So that's what you should always take a look at. But intuitively, this R-squared is definitely a very good and there's an intuitive metric for assessing the model fit. Is that in the sense that how much variation in an outcome variable is being explained by your explanatory variable. So here, I got all the information. I got TSS, I got RSS. So R-squared is simply the proportion of variance explained by your explanatory variable, or simply the ratio between the n-axis, model sum squared, over TSS, right? So we can actually do this in R. Finish this part and we'll do quick. Right, so again, we will still be using the same data set and so the same data before. So we first did univariate regression here by regressing cells on tracks. Okay. So how to calculate mean squared error? So the first thing to note so before you do that, you should probably take a look at not only what variable is inside the data, but also what element, or simply what kind of information can I get from my model output, which is LN fit, right? So if you enclose your model output inside a function called nans, it's the same function that you check the variable inside your model. You see, you have lots of information. We got coefficient, got residual, got effect, got ring, and fitted data. Fitted data is predicted data. So I can calculate random statistic from this, or simply by using some base R function. For example, by residual means, right? You can use those functions to do really simple numerical calculation. So in order to calculate mean squared error, the first thing you want to do is simply to get error, right? Or AKA residual. So we simply type residual from this model, your model output. Then residual sum squared, right? So I square that, and since the mean square error, mean, the first one is the average, so it's really take the mean out of it. And that's it, right? And root mean square